Good morning, folks. This is Mr. H here. Sorry I could not be in class today. You're going to work on some gravity calculations using Newton's universal law of gravitation, which we talked about the other day. So I'm going to walk you through two quick examples, just showing you, or reminding you really, how to plug in the variables into the equation, and then also how to use your scientific calculator to arrive at the correct answer. So watch closely on these two examples, and then after this, there's an activity that we'll have informative that you'll work through that will give you plenty of practice calculating the force of gravity. So for our first example, we're going to just calculate how strongly the Earth pulls on an individual. So of course, we know that if we're standing on the surface of the Earth, right, we know just based on the last unit that the Earth is pulling us down towards the center. Okay, and up to this point, we've just done f of g equals mg to find that, but actually, f of g equals mg comes from Newton's universal law of gravitation. So I'm going to go ahead and show you how to sub all of that in to go ahead and solve for the force of gravity between you and the Earth. So you can certainly plug in your own mass if you choose to, which would just be your pounds multiplied by 0.45. I'm just going to go with 50 kilograms. That's a nice even number for the sake of just being able to show you the work here for the mass. So we're going to do the force of gravity equals G, which remember is our universal constant, which is 6.67 times 10 to the negative 11th, times mass 1, which would be the individual, the human being. We're going to say that that's 50 kilograms, times the mass of the Earth, right? Because the Earth is the other object. So the mass of the Earth is right here. It's a really large number, remember, 5.9 times 10 to the 24th kilograms. So really, really big number here. So let's go ahead and put that in 5.9742 times 10 to the 24th kilograms. So there's the numerator of our fraction, and then we're going to divide that by the distance between you and the Earth. Now, be careful here, folks. When we're standing on the surface of the Earth, we are on the surface, obviously, so there's no distance between us and the surface. But when we're trying to find the force of gravity, the distance is the distance between your center and the Earth's center. So really, what we need to do here is we need to know the distance from you to the center of the Earth, or in other words, what is the radius of the Earth? What is that value there? So we're just going to give it to you. It's about 6.3 million meters. So we can go ahead and sub that into the equation, and then we can use our calculator and solve. So I'm going to go ahead and put the distance in scientific notation, which would be 6.371 times 10 to the 6th meters. And then we're going to square that thing, right? Because we have distance squared in the denominator of this fraction. So what is this going to look like? Well, we need to go ahead and get our TI-30s out to go ahead and try this. I would ask you at this point, if you don't have your calculator out, hit pause in the video so that you can go ahead and put all of your values in as I do it here and check your work. So we're going to first plug in the gravitational constant, 6.67 times 10 to the negative 11th. So that's just going to be 6.67 second EE negative 11 times M1, 50 kilograms, times M2, the Earth, which is 5.9742 times 10 to the 24th. So we hit second EE 24. There is the numerator of our fraction. And then we'll just hit divide. I'm going to go ahead and put my radius of the Earth in parentheses, which is going to be 6.371 second EE 6. Close it, and then I'm going to square it. Okay, we can't forget to square the distance that goes in the denominator of our fraction. Okay, so there is that x squared button on the left side of your calculator in there. Go ahead and hit that. So now we have typed in our numerator and our denominator. We can hit enter. It should divide it out, and we have our force of gravity, which is roughly 491 newtons. Okay, so 491 newtons. Now, how does that compare to our other method that we've used to find the force of gravity, which is, remember, just f of g equals mg? Well, f of g equals mg, our m is 50 kilograms, and G, we use 9.8 meters per second squared. If we do 50 times 9.8, we get, wow, 490 newtons. Not bad at all. So you might be asking, well, like, what's the difference between these approaches? Why is it when I just multiply mass by 9.8, I get this answer, and then when I do my mass times all of this stuff divided by this, I also get 490? Well, here's the thing, folks. No matter where you're standing on Earth, whether you're here at the bottom, east, west, over the ocean, it doesn't matter. Okay, you're always about this far from the center of the Earth. Okay, and the Earth, no matter where you stand on it, is always about 5.9742 times 10 to the 24th kilograms. So these two numbers never change. And you know what? G is a constant. That doesn't change either, guys. So guess what? If you do 6.67 times 10 to the negative 11th times 5.942 times 10 to the 24th divided by 6.371 times 10 to the 6th squared, you get 9.8. So all we've done is taken all this good stuff here, simplified it down to 9.8, and all you got to do, no matter where you are on the surface of the Earth, is multiply 50 times 9.8, and you're all set. Now, this only works for Earth because, right, that's the mass of the Earth, the radius of the Earth, and that's the mass of the Earth. If you go to a different planet, obviously, your numbers change. Okay, so there you go. We're going to do one more really quick here. This is just finding out how hard Jupiter pulls on you, because you are in the solar system, right? And everything in the universe that has mass has gravitation. So Jupiter, even though it's really far away from you, has gravitation. It is pulling on you right now. So we're going to go ahead and say that for this case, this is a little bit complicated because obviously the Earth is orbiting the sun and so is Jupiter. So our positions relative to each other are always changing, right? Sometimes we're pretty close to Jupiter, sometimes we're further. So we're just going to say that our distance from Earth to Jupiter at the absolute closest, when we're on the same side of the sun, is 6.3 times 10 to the positive 11th meters. So really far. Crazy far, right? We're talking about almost 1 trillion meters away. The mass of Jupiter is enormous, substantially larger than the Earth. It's 1.9 times 10 to the 27th. And let's go ahead and do 60 for our human being this time. So we'll go ahead and sub that all into our equation, right? F of G equals mg. I'm going to go ahead and do this so I have a little more room to work here. So we're going to do F equals our constant, 6.67 times 10 to the negative 11th, times mass 1, which is our human being, which is 68 kilograms. I thought that was 60. Sorry about that. Times the mass of Jupiter, which is a 1.9 times 10 to the 27th kilograms. Yikes, that is really big. Then we're going to go ahead and divide that by the distance from the surface of the Earth to the center of Jupiter, which is pretty big. It's 1.9 times 10. I'm sorry. Let me backtrack on that. It's not 1.9. That's the mass. It's going to be, 6.3. Whoops. There we go. 6.3 times 10 to the 11th meters, and we're going to square that whole thing. So now all we got to do is throw this into our calculator, and we should be able to arrive at the force of gravity between you and Jupiter when Earth and Jupiter are at their absolute closest. So 6.67 second EE, negative 11. Whoops. Let's see. There we go. Negative 11th. There we go. Times 68 times 1.9 second EE 27. So there's your numerator divided by, I'm going to put it in parentheses, 6.3 second EE 11. So that whole thing, and then squared. So there's your distance squared. So now we hit enter, and we get a really small number here, 0.0000217. So really, that's 2.17 times 10 to the negative 5th newtons. So pretty small, right? considering that, for example, if you're a 100 kilogram person, your weight on Earth is 1,000 newtons. Or even, if you're a 50 kilogram person, right, we just found that your weight is 490 newtons. So this explains why, although Jupiter is so much bigger than the Earth, okay, Jupiter's really far away. And Jupiter only pulls with a very, very small amount of gravity and is not able to pull you away from the Earth because the force of gravity to the Earth is substantially larger. Okay, so now what you're going to do is you're going to go into the formative. You're going to try the gravity equation practice. It works you through a series of practice problems where you have to show your work. And then also it will get you to start looking at the relationships between mass and force of gravity and distance and force of gravity. So go ahead and take the remaining time, jump into the formative, try all of the problems. And don't forget, you do have the final review WebAssign due next week, the reading guide due next week, and a gravity WebAssign due next week. Good luck. See you Monday.